Welcome. It's great to see so many of you here at the Isaac Newton Institute. For those who haven't met me, I'm Jens Markloff. I'm a mathematician from Bristol, but here in my role as president of the London Math Society and also as chair of the Campaign for Mathematical Sciences. As you all know, mathematics is under pressure. There are quite a number of math departments who struggle in their recruitment. And that's sort of a paradox because math is the subject right now that underpins so many of the exciting developments in our digital economy, from AI obviously, all the way to environmental sciences, epidemiology and so on. So I think we all share the ambition of making sure that our subject thrives without compromising on the beautiful math that we teach our students. I think we have a challenge in making the subject more attractive to a wider, more diverse group of students. And I think it's a good challenge, and it's nothing I think we should sort of shy away from. And I think part of what we're trying to achieve in these 2 days is to share our ideas, good practice, on where we think math education should go at higher education level. Part of the background for this is, of course, the Math Degrees for the Future initiative that was launched in 2024 with a call, and I was, and the whole campaign team was really absolutely stunned to see 34 applications being entered into the competition. The panel found so many inspiring ideas, and really, it was really very unfortunate that we only had 5 awards to give out. We're going to hear from the 5 award winners today, this afternoon. But it was never just about handing out 5 awards. It was much more. It was to showcase the beauty of mathematics, of a math degree, where it can take you, and really something for the entire math community. And part of the project Math Degrees for the Future is also events like this, where we want to bring everyone together and share all the other ideas. So it's not just about the winners telling everyone else how to do it, but really for us to come together and share the many other inspiring things that certainly the panel appreciated when they looked at all the submissions. So I'm really looking forward to an open discussion. This is called a community event, which means we haven't invited, maybe some are in the room, I don't know, but people who you might think, oh, I rather don't want to share that with them, so representatives from government or other organizations. This is really an open forum, so make the best use of it. That's my request to you. Obviously, also, I'm available, colleagues from the LMS and the CAMS team, who I'm grateful to for organizing this, as well as colleagues from the Newton Institute for setting this all up and working with us. So that's, I think, all I wanted to say. Of course, also thanks to XTX, who are funding both the grants, the awards, but also this event. And we are going to have 2 more events. Next year, we are planning an event which will involve external stakeholders. So this will be like, for those of you who have been at the Math Summit, it will be modeled on that. So we'll hopefully already have something to present that will come out of this meeting and to showcase. And then in the 3rd year, we'll have a final event, again, a community event to come back together and explore what we've learned, what has worked, what hasn't worked. And then finally, do also think about whether we need more funding. We were very fortunate to get £2.5 million as a private donation to support the scheme, plus extra funds to run meetings like this. But there's nothing that should prevent us from going back to our donor who supported this or other private philanthropy and make a case for funding along what we already have, or maybe variations on this. So please do keep this in mind, because money does help, in particular in the present day, where many of our institutions, I would say almost all of our institutions, are quite tight with money. And it does take resources, of course, to change things and to create new and exciting. So, without further ado, thank you all for coming. I'm going to hand over to Ulrike to also say a few words, and thank you, Ulrike, for hosting this event. It's a great place. I did my very first postdoc at the Newton Institute, and I've been back many times, and yeah, so for me it has a big place in my heart. So thank you.
Thank you. I think so. So let me also extend a really warm welcome to everyone from the Newton Institute, and also on behalf of the staff here. I'm Ulrike Tillmann. I'm the director here at the Newton Institute. It's the same, I like you mentioning that you have been here before. It's very much our hope that the whole of UK mathematics thinks of the Newton Institute as a second home for mathematics. So you're always welcome, and we always have an open door policy. So in case you haven't been here, let me just say there are toilets there and there. And in case there's a fire alarm, nothing is planned. We just meet outside the library. And I also want to just start with thank yous, namely this meeting brought together by a number of us, and I just mentioned Jens, of course, Mary, London, Kathy Hobbs, and also John Greenes, who I hope will join us later. I also want to thank the LMS staff, in particular Simon Edwards. It's always a pleasure to work with you, and Jennifer Gunn, who has helped, and here from the Newton Gateway, it's Claire Merritt, and also Annie Bacon, who you probably have met and exchanged emails with. Let me also thank in advance everybody who is going to present here. In addition, I would like to thank in particular those who have come here without possibly presenting. I think, as Jens already said, this is a community event, and it will be important that we come to some sort of consensus and have a conversation of what mathematics degrees in the future should look like. The health of higher education, mathematics degrees in particular, has been, of course, an ongoing concern for many years. As mathematicians, we are particularly interested in passing on our knowledge and keep the healthy culture alive, and in which mathematics can thrive. And it has to include research all the way up to primary school teaching, right? We also know that without a healthy number of students, university positions are difficult to maintain, which in turn will impact research capacity, and supply of teachers and students again. But it's not just self-preservation that we are concerned with. Mathematics, as Jens already said, is actually key also to the economy, as was confirmed, of course, in the 2013 Deloitte report, and again in the review of that report by the Academy. And indeed, some 20% of the GVA of Great Britain is attributed to mathematical sciences somewhere. That's a huge amount. So it really does matter what we do with mathematics. Though the concerns about student numbers is not new, and indeed, internationally it's everywhere. Just come back from Germany, they had worried about it. In the UK, it has intensified, I think, in the last 5 years in particular, with many departments being under threat. To a large extent, I guess, because universities themselves are under financial pressure. But I think in mathematics we had a particular wake-up call some 5 years ago, because Kathy Hobbs presented actually at the time a short paper to the LMS Council showing really how uneven student numbers are distributed amongst the universities. And some it had doubled, and some it had really gone to a very low level. Turns out it is actually this year the 10th anniversary of the removal of the student cap. In 2015-16, that was the first year when there was no student caps here in England. And that meant that, of course, quite rightly maybe, departments went and tried to make the best for them. So ever since the fees were actually introduced in 1998 in England, I guess higher education moved more and more towards sort of a free market model. And the removal of the student cap in that sense was just another step in that direction. And maybe, as one might expect under market forces, we have seen many changes. But even the most diehard Keynesian probably agrees that academia and the commodity of a bachelor degree in the mathematical sciences does not really fulfill the criteria to a free market approach being the most beneficial and produce optimal outcomes. On the one hand, the buying side, the demand side, we have students and parents and teachers. They cannot properly be informed to know what they are buying. If there were, they probably don't need a degree any longer, right? I mean, if you know what you get out of your, and indeed you need to know not just one degree, it's a whole lot of degrees you can possibly go to. And similarly, I think it's clear that any department is actually also not really in control of its commodity. It can change things a little bit here and there, but actually a university degree is much more than just learning some mathematics. And it's a complex thing, really. So planning has to come in. Resources are too scarce, really, that we can leave them just underused and wasted, and mathematics is too important, I guess, as a subject itself. If I may just take a sidestep here, the Royal Society has a committee, the Advisory Committee on Mathematical Education, and we will hear from them in a moment. The reason it exists, an unofficial reason, is that mathematics is too important to leave it to the mathematicians themselves, right? It's just, mathematics is just such an important subject that somebody needs to take care of it. I hope we can ask ourselves in this meeting here not only how mathematics degrees have to change and move forward to provide students with the necessary skills they need in the future, but I hope also that we can think about how, as a community, we can help each other in the country to make the most of the capabilities that we have. What are the tasks? We need more math teachers. It's terrible, actually. Every year, thousands of teachers, the recruitment is below the target by 1,000. And indeed, about 50% of all math teachers quit teaching after 5 years. So it's a huge waste of energy and resources. Of course, the economy depends on mathematical sciences, and so we need to not just have math as we know it, but we need to also make sure that students know the new science, and whether it's data, machine learning, and AI. But so we must examine whether our degree courses are still really teaching the right content and equip students with the right skills. But for me, there's another important part is that we need to enthuse, of course, also students about the beauty of mathematics, and to make sure that if they come with a passion, that we give them the right courses and they can develop that as well and become possibly mathematicians. Okay, in addition, I think there are very much important non-mathematical skills that we somehow need to bring into a master's degree. There's no point in having a light and putting it under a shovel. So you have to be able to also communicate whatever you find to a broad range of audiences, whether it's a technical audience or a more common audience. I mean, that's one of the reasons here in the Institute we have, over the last few years, put a little bit more emphasis, well, quite a bit more emphasis on communications itself, and had various communication events and fund a network. It's also one of the reason I'm here, in a sense, namely, how can one somehow promote communication in the context of a degree course? And I think it was actually exemplified for me by a short talk by Paul Glendinning, who's in the audience. He gave a very short talk to the Hoddams meeting a year ago. And it seemed to be just the sort of thing that we need, namely to push students and to make it clear to them that actually communicating the mathematics and convincing with the mathematics is just as important than producing, in some sense, the science behind it. So I'm very happy to be here as one of the co-sponsors, co-organizers of this meeting, and I'm very gratefully accept also the financial support from the LMS. It's wonderful to, of course, to celebrate at the same time the successes from this competition, and my warm congratulations to the winners here. And I just hope for today we can keep certain things in mind, namely, where do we need to move with mathematics in higher education? How can we ensure teachers are equipped with the math they need? And that's not just math teachers, potentially. And how can we work together to ensure local and also national adequate provision? One thing that inspired, I talked to somebody last week who was an eminent Dutch chemist. It was quite inspiring. They actually, it's a small country, so they decided they have 11 universities. They divide the physics and chemistry, that's what he talked about, the subject areas amongst themselves, and so that not universities compete within Holland against each other, but yet at the same time they have provision of all of the different subject areas in the country. Now, Holland is a much smaller country than the UK, and there are other forces, and research is another thing than teaching. However, I think it is an example where self-organization is important. So maybe we shouldn't just leave it to others. Mathematicians shouldn't leave it to others to organize ourselves, but maybe also we should try to organize ourselves. Okay, so with that, I just want to actually start our meeting. Look very much forward to it, and would like to call on the first speaker. So Paul Wakeling from University of York is going to give us a talk on a geometry of mathematics in higher education.
Thank you very much, Ulrika. Okay, thank you very much. So I'm an interloper here. I'm not a mathematician. I'm actually a sociologist. And usually, if you invite a sociologist along, they're going to be provocative and say something that's going to wind you up. But I'm not going to do that today. I'm going to really just describe what I've observed of the size and shape of mathematics in higher education. So this is mainly a descriptive talk to give some statistics to things that you might anecdotally understand, and perhaps there'll be one or two things in there to challenge you as well, or to challenge what you understand as well. So I will be concentrating on how many mathematicians there are in higher education at undergraduate level, who they are, what their kind of background is, and a little bit about where they're studying as well. And then also saying something about what happens after a mathematics degree briefly. And Ulrika was just mentioning the importance of school teaching for the kind of mathematics pipeline and the circulation of mathematics. So I'll say a little bit about that. And for brevity's sake, I'm focusing today only on undergraduate students, which I think will probably be the bulk of what the discussion is about over the next couple of days. But if you are interested in postgraduates, which is really more my chosen specialised subject, then do look at the two of the reports that I'm going to flash up in a moment. Again, concentrating just on first year enrolments to see what new is happening from year to year. And the data that I'll be presenting initially runs from about 2010 through to about 2022. So the last couple of years are missing. Of course, it's not possible to get data about the year that we're now in yet, although I imagine that'll be something it'll be interesting for you to talk about, because it's been a very turbulent year at undergraduate level in terms of entry. What I'm talking about today draws on these two reports on the right, and this is really part of a suite of 4 reports where I think the campaign has a bigger or smaller hand in the production of those reports. So I'm personally very grateful to the campaign into LMS for supporting the research that was in my 2 reports. I'd also recommend to you Andy Noyes and colleagues' report on the mathematics pipeline in England, which really tracks students through from Key Stage 1 in primary school through to the end of compulsory schooling, and has some really interesting data, particularly about boys and girls and how they dip in and out of mathematics at different levels of attainment and at different places. And a report by Autos Economic Research, which some of which is similar to what I looked at in the green report there. And just about all of this draws on Higher Education Statistics Agency data, which is the administrative data that's collected from all of our students when they register for their courses. The first thing to point out then, this has already been mentioned, that mathematics has not really seen growth in enrolments at undergraduate level in a time when overall enrolments in undergraduate education have increased. So the top dark blue line is for the right-hand axis and is showing you overall growth of first year entrance to full-time higher degree, first degrees in the system. So it started off at about 400,000 plus students, and it's gone over to 500,000 over that 10-year period. At the same time, maths, which is the green line, pretty much flatlined, went up a bit, came down a bit. So while there's been growth overall, maths has held its course really, which in relative terms is a slight decline. And that's probably, out of the set of comparator disciplines we were looking at, physics, IT systems and computing, and economics, probably the least of growth in mathematics of those subjects. IT tracking the overall trend. Ulrika was talking about distribution of physicists and chemists in Holland. If we look at where mathematics degrees are studied, we can see that there are areas where mathematicians are under and overrepresented. So in London, the northwest of England, Scotland and the northeast, there's an overrepresentation of mathematics entrants compared to both the general population and the population of younger people as well, and all first degree entrants. So London, particularly strong concentration, and other areas where there are far fewer mathematicians than we would expect, which includes where we are now, the east of England, where Cambridge is, Northern Ireland, Wales, and unfortunately for me, Yorkshire, which is where I'm based. So not an even distribution of mathematicians across the country, and definitely not an equal distribution of mathematicians across institutions. So Here we have the institutional location of new first year undergraduate maths students. The dark blue is the Russell Group. The green is other pre-1992 universities. So together, you will estimate this better than me, but it's over 3/4 of mathematics undergraduates in the old universities and a much smaller representation in the post-1992 sector. And you can see some names there with very big numbers of students. The OU being the biggest, but some of the older, the Russell Group universities having large registrations. That contrasts sharply with the overall distribution of undergraduates in any subject, where post-1992 institutions have about half of the new first-year enrolments. So mathematics is very much an old university subject. It's very much a Russell Group subject, and there's evidence that it's becoming more so, and it'd be interesting to discuss that either amongst yourselves or with me later, whether that's even more sharply appearing this year. Certainly if we track the change in registrations over the 10 or so year period that I was looking at, you can see that the growth is all in the purple bars, or nearly all in the purple bars. That's not the Russell Group, it's high tariff universities. So universities which have high A-level demands or similar, that's where the growth has happened, and the institutions that have lost numbers are generally those from the medium and the low tariff institutions. Everybody now is desperately trying to turn their head sideways and see where their own institution is. But if you want a closer look, this is in the blue report in more detail. And I expect if we had this year's data, we would see that trend even more sharply, and some of those bars would jump up quite a bit from conversations I was having earlier. Now, this is one of those charts that probably comes around about 4 times in a career, where you run it and you think that can't be right, and you run it again and you still think it can't be right, and then you run it again and it is. This is looking at who studies maths, and looking in particular at socioeconomic background. The pie charts are showing you that, no surprises here to anybody in the room, but students doing maths in Russell Group universities are much more likely to come from upper middle class backgrounds, professional and managerial occupational households, than students in post-1992 universities, and the ones who are at non-Russell Group old universities are somewhere in the middle. That's not a really surprise. Anybody who knows anything about higher education participation would be able to tell you that. What was a surprise to me is if we look at who the new students are, where the growth has been in terms of categories of students over that 10-year period of showing you in maths, almost all of the difference is in students in professional, managerial, occupational background homes in Russell Group universities. So it's very much a particular set of people who have been the difference in where there has been growth in maths, that small growth in maths that we saw. I'm going to shift now to talk about what happens after a first degree. So these are graduate outcomes for students on a 3-year BSc in maths and an integrated master's. For maths, that would be an MMath. We've also got MPhys and MSc students here as well. So these are undergraduate master's students and bachelor's students. Not a lot to tell you about these charts. So maths graduates in terms of further study or employment are performing around the same as students in similar disciplines. I think physicists do very slightly better, but there's not really any clear trend. There's not a lot to say from that, other than that graduates in those 4 subjects do better than graduates in other subjects on average. Again, that's probably no surprise to you. And maths graduates go and do a lot of interesting and varied things. So they are found in all of the sectors of the economy, but concentrated in 4 areas in particular: in scientific and technical, financial, informatic, and education sectors. Okay, again, no great shocks. I told you I wasn't going to be very provocative. But perhaps more interesting is the detail of what they do. We can see we've got about 1 in 8 mathematicians goes into some sort of programming and software work. 8% become secondary school teachers, and we've got people working in the finance sector as well as actuaries, statisticians, investment analysts, accountants, and so on. So they remain popular destinations for mathematicians, and perhaps that would be something to think about as student choice seems to be hardening around return on investment kind of study decisions. Mathematicians also have very good professional outcomes relative to other subjects, so they go into further employment and that tends to be good employment. Unfortunately, the data doesn't allow you to discriminate very much among wage levels, so I was only able to tell you the median salary, and that's the median salary for most subjects. So not a great deal to tell you about there. What is interesting is if we drill into this data a little bit more. So two different charts here telling you quite different things. So the first chart on the right is comparing where a student did their first degree compared to where they ended up working. And there's a very clear story from this, which is a brain gain for London and a brain drain for just about everywhere else, apart from Scotland, which just about holds its own. So mathematical graduates tend to move to London. All the roads lead to London, probably paved with gold. If you're going to London, you'd hope they are, because you're not going to be able to live anywhere. And don't forget that we started from a position where there was already an overrepresentation of first degree students in London. So it's an additional concentration on top of that. And I think that is something that, again, connects to what Ulrika was saying about where people are based. The other chart is showing us people going into school teaching. And if we compare mathematics to physics, to computing economics, so similar subjects, maths graduates are much more likely to enter educational employment. They are more likely than the average graduate to go into school teaching, not primary, but definitely into secondary school teaching. And I would say really that in terms of the graduate destinations at the moment, given the students that we have, that looks like saturation to me. That looks like it would be difficult to improve that progression into teaching without changing who is doing maths degrees. And I think the next page shows this in a little bit more detail. So I broke out here the background characteristics of mathematical graduates who enter educational work by ethnicity, gender, institutional location for their first degree, and socioeconomic background. And certainly with the socioeconomic background data, it's showing you that more disadvantaged students are more likely to go into teaching than more advantaged students, and students from the post-1992 sector are much more likely to go into teaching. But of course, we've just seen that that is the very sector that seems to be shrinking. So that is really sort of bad news potentially for the future education workforce, where we're already hearing we've got thousands of shortages of maths teachers. Okay, I've thrown a lot of numbers at you. Usually with an audience just after lunch, that is enough to send them to sleep. I'm probably in different company here, so hopefully you've taken some of that in. Just to summarise then, very little growth in maths, unlike what we've seen at school level where A-level's really taken off. We've got this regional imbalance in mathematics education. We've got a concentration, an unusual concentration in high-tariff Russell Group universities. An apparent concentration among the socioeconomic advantage, and that's becoming more so. Whereas maths graduates have good outcomes, they're generally getting employment that's relevant to the sort of things that they've been doing, but they're more often going to London to do that than not, by the looks of it. And we may have some challenges ahead further challenges ahead in recruiting mathematical teachers. Thank you.
We might have, well, a quick question now, maybe.
Thanks for that. I might have been asleep for the last slide. So I got confused because we've got two things going on. We seem to have saturation of the number of undergraduates moving into teaching, but not enough teachers.
Yeah.
So how do those, was that the last slide?
Yes, essentially that's the case. I think what I'm saying is if you want to get more teachers, you're not going to be able to get them out of the existing maths population, because it looks like you've probably gone as far as
percentages rather
more
than
maths are going graduates are going into teaching than in other subjects. So you either have to change the composition of the maths undergraduates to be more like the people who do go into teaching, or just get more maths undergraduates, which is, I think, something you're interested in anyway, right?
Great, thank you very much. So our next speaker is Courtney. Wait, hi, Kaina. She's from Purposeful Ventures. What will happen to the number of university math undergraduates?
Hi everyone. It's such a pleasure to be here this afternoon with everyone. Today I have the opportunity to build on what Paul spoke about and speak about what could happen to the number of UK undergraduates who are taking maths going forward. By way of background, my name's Courtney. I work at Purposeful Ventures, which is a not-for-profit. We partner with both social entrepreneurs as well as philanthropists to build new charities, as well as to help accelerate existing charities in the market. And through that, we're really focused on how do we give young people more opportunities in education, and really an area that we share with, I think everyone in this room is a real passion for maths, and how do you really strengthen that pipeline throughout. So it's through that work that we've been partnering with the Campaign for Mathematical Sciences to do some of the research that really is the call to action for how do we build up more maths undergraduates and how do we build that pipeline going forward. It was about a year ago, we partnered with Data HE. And for those who haven't worked with Data HE, they're a consultancy that works with a lot of universities as well as the sector to be able to use data to either drive enrollments or look at what's happening in the sector. And what we did together was look at, well, what's happened to UK undergraduate enrollments over the past 2 decades, and therefore what can we believe might happen going forward if nothing changes. And they ended up building a model, and it did 2 things. One was forecast the pool of UK undergraduate students. So it looked at historical trends on the percentage of people pursuing a higher education, and that was by age, region, and sex. And it was from there that they built that up and married it onto the population projections to be able to see that pool of undergrads. And then they also looked at what's the forecasted, or what's the historical preference for maths. And then if that was to continue at similar rates within the age, sex, and regions, how does that play forward? So that's what you'll see today. They very much took a roll through, so they used the historical trends and continued those forward, which is quite a blunt instrument, but I think it's a really helpful if we step back, maybe not from the specific numbers, but look at the trends to say, well, actually, if nothing changes, what would happen? So I think it's more probably a call to action and kind of the degree of direction rather than the specific numbers that will be helpful here. And throughout this presentation, I think it's great that Paul just went, because I'm taking for granted the fact that everyone in this room, that we've already seen the value of math, so I'm not going to talk about why it matters to get more students in. So I guess what's happened, or I guess maybe I'll cover first what I'm going to discuss about. One is just the number of historical undergrads. I'll then talk about what's driven this change historically. Then what's expected to happen going forward. How has maths fared versus other similar subjects? And then lastly, some of the implications for universities. So this chart here, what we're looking at is the number of just UK students. So we're not looking at international for the sake of this. This is UK entrance to undergraduate maths courses over time, over nearly the past 2 decades. And as you see, it's definitely not single trend. Lots of things are happening. But between 2012, or when the fee cap was lifted, until 2018, you see a pretty steady increase, followed by a slight decline, which was when the curriculum changed in 2018. I think the hypothesis there is that could have been partially driven by the lower share of high A-level grades for maths. And then since that, you've seen the number kind of remaining steady between 7.2 and 7.4 thousand entrants into maths. Overall, though, what's happening here? So if you look, it's only a 200 student drop or entrant drop over the 2 decades. But what you're actually seeing historically is this is the percentage of UK undergraduate entrants studying maths, so kind of the preference for maths. And what you see under this data is there's been some bumps, but a fairly steady decline in that rate over the past 2 decades. And what this has been, it's been masked though by the fact that more students are going to university. So that those two trends, what feels flat has been masking this decline over time. If you were to roll this forward, and I think this is the very kind of blunt approach, you would see a potential. So the gray line is the modeled line versus the orange being the actual. You could see a potential decline. And actually, this is really the call to action. I know everyone's in this room thinking about how do we change that and how do we create programs that really are able to slope that up. If we then think about, well, what happens going forward? So if we look at just first of all, the last 20 years in terms of the contributions. So in terms of the 200 students that have been lost, what you see is population hasn't contributed that much to the change. Instead, what you see is the HE entry rate. So the percentage of folks that are going to university has increased massively, which has then been countered by that fall in preference for maths, which then leads to a pretty flat number there. If you roll this forward, the next 6 years are estimated to be quite flat as well, if nothing changes. And that's because you do see population, you see benefits there as the population of university-age students will continue to rise. There should also be the benefit of more students going, or more university-age people going to higher ed, and then that will be countered by the fall in preference. However, in 2030, the population of undergraduates is expected to start to decline. And at that point then, the acceleration, you can see an accelerated decline in maths if we don't change that line and that preference. So if you roll that forward, you could see quite a material decline. In terms of what's been happening between the subjects, what you see here on the left-hand side is the historical, and that's the absolute change in number of undergraduate entrants into maths. And we're just looking at some similar other analytical subjects. But what you see is, while math saw a small decline, you see that economics, finance, and computer science saw a relatively large increase over the last 20 years. If all of that just plays through as is, and I know that there will be a lot at play, and that actually it's all of us that will have the ability to change this, but just by the data, economics and finance will continue to see those gains over the next decade, with math seeing a continued decline as well as physics. And I think another interesting point here is within the historical data, you also see that there has been a fall in single subject maths. So 75% of math degrees were single subject in 2012, falling to 65% in 2021. And then in terms of the actual universities, Paul definitely covered some of this of the concentration. But what you see since the release of the student number controls, which would have been in 2015, you do see a concentration. This is the percent within higher tariff, medium tariff, and lower tariff universities. And you see between 2006 and 2024 an increase in the higher tariff penetration from 56% to 66%. The data doesn't suggest that this will continue. However, if you were to see more departmental closures between the lower tariff and medium tariffs, that could cause that to continue. So with that, I think there's five learnings from this. One is just the fact that there has been a very modest decline over the last 2 decades, the fact that that's been driven really by the preference for math, but masked by the number of undergraduates rising. If nothing changes, then actually this could be seen to accelerate after 2030, so really the call to action in the next 5 to 6 years. And also an opportunity as maths loses share to adjacent subjects of actually, well, how do you bring people into the foundational maths that's going to give them the ability to go off and do any of those careers that those other degrees do? So there is a lot to play for and a lot of interest in this, as well as then the concentration in higher tariff universities. And I think also what we have seen is the teaching staff disproportionately comes from lower tariff and medium tariff universities. So actually just the real importance of not losing some of that share of those universities as well to be able to fuel the next generations of students. I'll leave it at that.
Thank you very much. Two very interesting talks and thought-provoking in terms of numbers. Questions?
Oh, I probably should.
Thank you, Courtney. Is it true that maths numbers popped up this September by a quite significant proportion?
Yes.
How does that affect you?
Yes, I think it's a great question. I think the answer is, I don't know. It seems like so I should have said that this data is a mix. We looked at both HESA and UCAS data. HESA is a much richer data set in terms of subject level, but UCAS obviously is the ability to look at more recent data, and it would have been the UCAS data that saw a significant blip up. I think the answer is we don't quite know. Is that noise? Is it just a year? What is underlying and driving that? So you hope that that actually means a more positive, sustained preference. But I think it's going against the trend.
If I was going to push you, do
Yeah.
you have a hypothesis?
I don't. I think I was speaking to Paul about this earlier. I was like, what is driving this? I spoke to the data AG team. I think one thing they're thinking is, could this be more folks going into like AI maths courses? But I don't. You probably have a much better sense on the ground, seeing what students are seeing, or seeing the students that are coming to you. So I think it's to be determined. And I think it's one to keep watching.
I'll probably have to leave it because, sorry. Thank you very much again. Our next speaker will be Catherine Boulton from the Royal Society on the Mathematical Futures Programme, the Royal Society's vision of mathematical and data education to age of 18. I'll just take advantage and say hello to Jane.
I'm going to say a few words as well. It's going to be a tag team talk.
Sorry?
It'll be a tag team talk.
Oh, okay. Fantastic. So anyway.
Great. Hello everybody, and thank you very much for the invitation to be here. Thank you to Ulrika and Jens and to Simon, who I know I made send a lot of emails to clarify what we were supposed to be doing today, so thank you. As Ulrika said, I'm Kath Boulton, working at the Royal Society, and I'm going to go completely different. We're not looking at undergraduates. We've been looking for the last few years at what happens before then. What happens in the ages of compulsory schooling in this country anyway, from 4.5 to the age of 18. So I'm going to tell you a little bit about the Royal Society's vision for mathematics and mathematical and data education, as we've rechristened it, for the future. It's been a big project, and Jane's going to tell us, following the publication of the project last autumn, 2024, Jane's going to tell you what we are going to do next. I'm going to try and describe how we've got to where we think we want to go, if that's not too convoluted. So first of all, why the Royal Society? As Ulrika said, the Royal Society, somebody, I think it was Frank Kelly actually, who some of you may know, said that mathematics was far too important to be left to the mathematicians. By that, he wasn't being dismissive, he was just meaning that maths is everywhere. We've already heard a little bit about that and how important mathematics is. And so although the Royal Society, as I'm sure most of you know, needs no introduction as the National Academy for Science, in this context, science means much more than chemistry, physics, biology. It includes mathematics, and mathematics is a key tool for a lot of the exploration, endeavour, and academic outcomes that the Fellows of the Royal Society and beyond are involved with. So, the Royal Society, as well as looking at the kind of frontiers of science, the Royal Society has actually had a very long-standing interest in education, i.e. education pre-university. I thought those of you who are affiliated to the London Mathematical Society might appreciate this quote from nearly 200 years ago, where it talked about the importance of mathematics and physics of the highest concern to a commercial and manufacturing nation. There's some wonderful pieces in the archive which echo other thinking around why mathematics is so fundamental, not to mathematics as a discipline, but beyond that. However, we could dwell on that for a long time. I've dug into the archives quite a bit, but I won't. What the Royal Society decided to do about 5 years ago was look at what should mathematics look like for the future. Digital tools are everywhere. Data permeates every aspect of our lives. So a programme of work was set up with funding by 3 major companies, Google, GlaxoSmithKline, and Arm. They all saw the need for more data in education. It was really, really important to them to have potential employees who understood how to use data in creative ways. Ulrich has also mentioned the Royal Society's Advisory Committee on Mathematical Education. And so that body took on the responsibility of managing a programme of work to answer these really big questions. So they're not easy questions to answer, as I'm sure you'll agree. So we looked a long way into the future, 20 years, it's only 15 years now, because we've taken a little while to do this. So asking, well, what mathematical competencies would young people need when they emerge from that compulsory education system to thrive? And what does society need from those young people as well in order to function? And in a sort of governmental sort of terms, in terms of the economy to grow. And then possibly the even more difficult question, how does the education system develop those mathematical competencies? The education system is really complex, again, as I'm sure you know. And if you try and change one thing, you have to change a whole load of other questions and areas of it as well. So you can't just put in a new range of qualifications and hope that that fixes magically the whole system. You've got to work across the whole curriculum, across teacher education, across support and the assessment framework that you are working to. So it's a big set of questions to answer. We did a lot of research. We commissioned our own research, and we drew on a really wide range of other expertise and evidence in order to inform our thinking. And we came up with this, which we called a new approach to mathematical and data education. So we rechristened mathematics in the school sense, school and college sense, to mathematical and data education. And the shorthand for that is MDE. We also thought about, well, who is this for? Who are we providing this education for? And yes, it's really important to have the highly skilled elite mathematicians of the future, but also everyone else needs to know about maths too. Everyone else needs to be able to understand data. And that's built into the thinking. I brought some copies of the report, exec summary. Some of you might have picked them up, but it's all online. The whole report is quite chunky. But it's quite pretty. It's quite nice if you want to have a look. But it's all online. You can download it from the Royal Society website if you just put Royal Society Mathematical Futures. So what was our conclusion? We have a very nice report, but that's all very well. What did it say? So we said that the scope of mathematics needs to change. It needs to broaden to be what we've called mathematical and data education. But what does that actually mean? We said it needs to combine maths, what we could traditionally think of as maths, with some elements of statistics, with data science, and pretty much equally importantly, it needs to incorporate the computational tools and digital technology that we felt perhaps weren't best used in schools and colleges as much as they might be. But we went beyond that. And we said this has 3 key components. First one is what we called foundational and advanced maths. So in some contexts, we've used a shorthand to describe that as being the toolkit, the mathematics that you need, both as fundamental understanding from an early age, and then which builds up into the highly proficient advanced mathematics at A-level, into university and postgraduate level. Everybody needs a bit of that. General quantitative literacy is kind of how you use the foundational elements of those maths and data skills in everyday life. How you discern mis- and disinformation and don't get misguided into making poor decisions, for example, in personal finance. Everybody needs some of that. No matter how brilliant you are at the technical aspects of mathematics, you need to know when and how to use that in your everyday life. And then we had domain-specific competencies, so where the maths you use might be very specific to a particular discipline. So the maths you might particularly need to use to analyse a set of data in psychology is going to be a little bit different from what you use in biology or medicine, for example. So those are where maths is used in a very particular way for a very particular set of learning. And the key thing is that every young person needs some of all of these. But the balance between those three is going to be different depending on the route that they take beyond their school or college education. If you want to know a little bit more about how we think those three areas of learning look like in examples, then there's some more detail in the report. So after we'd done this thinking, and believe me, it took a lot of time to come up with those 4 words, mathematical and data education. It was really difficult to agree that that represented nearly 5 years' worth of thinking and research. So we came up with some recommendations. The idea of a task force was put together before the curriculum and assessment review, which a lot of you will be aware was published by the government week before last on the 5th of November. But we'd still like to kind of grab this issue by the grab it and take it forward. And we feel that the Royal Society will be really well placed to do this because we are looking beyond maths for maths' sake, which is really important, but we're seeing it in a context of a much wider world. That's still a little bit TBC. We really feel strongly that the curriculum needs a rethink, and probably beyond what the curriculum and assessment review suggested are going to be the changes that happen in the next few years. That it really needs a thorough unpicking to look at where maths and data applies in lots of different areas. And particularly, it gets neglected sometimes, but particularly going back to those early years where we recognise that spatial reasoning is often displaced in favour of number in those early years, but actually it's really valuable in terms of building strengths and skills and understanding that you need later on. So then alongside that, plainly, you need to be able to know where young people are at, you need to be able to assess them, and they do, like it or not, need some kind of passport to go on to the next stage of their journey in life, which usually comes in the form of some kind of examination. But we also, that developing new methods of assessment implies using perhaps some digital tools a bit more, working out how you can assess some of those data skills beyond pen and paper, which is the current method, more or less universally. This is where the computational tools and technologies comes in, to use that to enhance teaching and learning and understanding, most importantly, at every stage, because that's what we use in work. That's very few people who don't sit in front of a computer at least some of the time, or in front of a phone to calculate this, that, or the other. And that they need to be familiar with the relevant tools for the relevant problem to help solve that in daily life and in work. And then finally, but most importantly, teachers. We were talking about teachers a few minutes ago. They are a key part of the system, and we're short of maths teachers, we're short of highly skilled maths teachers. We know that they don't stay in the profession very long, even if the recruitment rate from maths graduates is relatively high compared to other subjects, and they need to be able to have some agency. Those teachers need to be able to have some input into what they're doing and not be passive recipients of a curriculum or a lesson plan. So we need to value them, and maybe they'd stay a bit longer if we valued them a bit more and made that really clear. So there's a big set of recommendations. The devil is in the detail, as always with these things. But overall, we want to build confidence. So, and again, a lot of you will know Adrian. That's a very fuzzy picture. A lot of them, you will know Adrian Smith, soon to step down after his time as president of the Royal Society. But we hope that if we can get young people to understand mathematical and data education isn't just long division or whatever their preconceptions are, we'll change the culture around maths and help to mean that they can enjoy it as well as use it sensibly in a lot of different environments. So that's what we concluded. Jane is going to tell us, as chair of ACME, how we hope to reach that destination, what we're going to do to take it forward.
Thank you, Catherine. Yes, thank you. So this report was published sort of in the middle of last year, and we need to pay absolute credit to those. So there are people in this room who were involved in writing that report, and people from ACME in this room who are know more than I do about where this report came from, because I only started this January, and have been involved in trying to work this forward since then. So I was brought in to replace Martin in the beginning of this year, and I am also not a mathematician. I'm also was a school teacher. I'm an emerita professor of biophysics in a chemistry department. So I'm a mathematical scientist. But I didn't start my PhD till I was 40, and before that I was a school teacher teaching science. But of course I was one of the many people, one of the more than 50% of people that teach mathematics in schools who's not a mathematician. So I do have that background in mathematics, but also throughout my research, I've used mathematics the whole time. And I absolutely appreciate why mathematics is important. And hopefully my role is to be able to explain to power that maths isn't just for nerds who sit there and don't talk to you. Maths is for everybody, and how we can make sure people understand the importance of that and try and enact some of these. Well, the great thing was, shortly after this report came out, we got a new government and they said, we're going to review the curriculum. Woohoo! Off everybody went. Many of you in your organisations were there, involved in writing to the curriculum review and explaining. And we were very confident that this report, which was so well researched, had the support of so many, would really influence the outcomes of this curriculum review. And it was part of the whole Royal Society's thinking about a broader, more balanced curriculum across the school years. Everybody should be doing mathematics all the way till they're 18. We should have the relevant kind of mathematics for everybody all the way through. So it's not unfair to say that although the government decided that they would go ahead and do this review, and they had this manifesto commitment, it's going to be great, this mathematics, this was entirely underwhelming, this report. And this is a quote from Ulrika, who signed off on the mathematics part of this report. But the whole thing was disappointing as scientists, as well as people wanting there. She said that, we recognise that the report says it's got an ambition to support maths, but having an ambition, saying we are ambitious to do this, and then doing nothing, is not a real ambition. You can read her things. We talked about the importance of the post-16 world. A third of our young people fail maths in 16. It's all very well seeing those great trends of more and more people doing maths A-level. They're all doing it because they want to be doctors or bankers. They're not doing it because they adore maths. And our young people need that confidence. So we need to really think about what we're doing in schools and in mathematics. I see somebody's here from the IB. Somebody I noticed on the thing. The schools just take away the funding for IB, which is something the Royal Society's been calling for more of. It's just gobsmacking. And there really is there's no quick fix to this. How often do we have a proper curriculum review and then to lose that opportunity to do something important is very, very disappointing. So ACME has decided that what our job is to do over the next few years is to try and realise that the vision that was in that report on mathematical and data education that our children deserve. The government talks about needing maths, needing data education, preparing our children for the data-rich world of the future. The words data is used in two places only. They keep saying the data show, blah, blah, blah. But in two places only in this curriculum review. One is in geography, good for the geographers, recognising they need to understand data, and one is in computer science. Not mentioned once in mathematics, not mentioned once in science, the need for a good data education. So we've decided that our job is to try and influence the next steps of the curriculum review, to try and push back in that poor vision and get far more understanding of the fundamental role that mathematics plays. to do research and proof of concept projects to show what could be done if we work this way, what could be done, what could be achieved. To collaborate and support, which is why I'm standing up here today, with the wider mathematical community. Because we're going to need to work together if we're going to make any difference. What was depressing in your figures that you didn't show is how few of the people that do maths go into the civil service or in the government. You know, count the number of mathematicians in the civil service or government. You know, you don't need an abacus, you probably need a hand. Involving teaching in the co-creation of this system. You know, ongoing review, recognising from what you say that until we get more people doing maths at school, therefore more doing maths at university, therefore more maths teachers, this vicious cycle of loss, we need to educate non-mathematicians to instill a love of maths because they're teaching it. The primary school teachers are teaching it, and very, very few of them have got maths beyond GCSE. So we need to support further curriculum development for them. And how can we do this? And then keep up the demand for a broader post-16 education system that really works for them. So I'm here to say thank you, all of you, because you are my sort of the heroes of this thing. You're creating these people that we need, and asking you to support us, the Royal Society, to try and get this message across where we can, to as many people as we can. And when we come to you to ask to help with research into some of these aspects, we can work together so that we're all giving the same message across. And again, to those of you in the room who contributed to this report and who are working with ACME and who are my colleagues now, that's wonderful. Anyway, thank you for having us at your meeting today. Thank you. Do pick up copies of these, or it's online. You can email me or Kath and we can send you a link. Thank you.